Okay, welcome. So, we have been now equipped with the basics and fundamentals of PN junction, of Schottky junction. We have studied most of the carrier transport processes and phenomena, things like mobility, velocity, drift, diffusion, continuity equation, traps, recombination. All these things are something that we are familiar with. Okay, the basics of that we are familiar with. What is the next step now we do? Because we have understood PN junction and Schottky junction well, the next natural course of action would be to study transistor. Okay. There are many kinds of transistor, and we will start with bipolar junction transistor or BJT, because that has a lot of similarities with PN junction. In fact, it is a PN junction in some way. Okay, two PN junctions. So, a bipolar junction transistor, if we study and understand it thoroughly, we can understand almost any kind of transistor. Okay, and for thereafter we will go to MOSFET and other kind of transistors. Okay. So, today's class we will start bipolar junction transistor. We will give a background of what a transistor should be, or is it, what is a transistor, what is the function of a transistor, and what is so good about bipolar junction transistors that we have to study, and we will come to the Venn diagrams and the physics of bipolar junction transistor. Okay. So, we will come to the whiteboard now. So, you have definitely heard the word transistor. Okay. A transistor is a 3-terminal device, broadly and loosely speaking is a 3-terminal device. So, essentially if you have a point A and point B, the objective of a transistor is that, see, in general the current that flows between A and B is controlled by the voltage that you are applying between A and B, right. That is, either it is linear, which is Ohm's law, it may be non-linear, does not matter, but in general universally the current flowing between 2 points A and B is controlled by the voltage between the 2 points A and B. But in transistor the objective is that the current that flows between points A and B should be independent of the voltage that you are applying here within some range. Okay. So, that means does not matter whether you are applying 5 volt or 10 volt or 20 volt or whatever, of course there is a breakdown, but within that limit, say 5 volt and whatever, you are changing the voltage between A and B points. So, I am writing it VAB. So, you are changing the voltage between A and B. Okay. But the current that flows between A and B, okay, the current that flows between A and B should be independent of the voltage you are applying between the 2 terminal, which means the current, if I plot the current voltage characteristics, it should be flat. Okay, which means it is 0, suppose this is 1, this is 2, this is 5, this is 10 volt, does not matter what voltage you are applying between this and this point, the current that is flowing is constant. Maybe suppose this is 20 milliampere. So, it is current constant, current is flowing. Okay. Of course, at 0 it has to be 0. So, it will come down to 0 like this. Okay. It will come down to 0 like this. What is controlling then? What is controlling is actually a third point, C. Either the voltage you are applying at C or the current you are feeding in at C should control the current between A and B. So, if I am increasing the voltage at C point Vc from say small 1 millivolt, 2 millivolt, I am increasing, this current should keep changing. So, this suppose this particular plot corresponds to third point, a third terminal I am applying a voltage, suppose I am applying 1 volt. So, this corresponds to Vc equal to 1 volt, third terminal. Okay. So, if I increase Vc equal to 2 volt, this current should also increase. Okay. Vc equal to 3 volt, this current also should increase, and Vc equal to say 0.5 volt, this current should decrease, but they should all come to 0 at 0 volt, right. So, like that. So, you see the current between 2 terminal is independent of the voltage between the 2 terminal, but it depends, you see, I am changing the current from this to this to this to this by changing the potential at a third point, or maybe the current that you are putting at third point. This is transistor. Okay, this is a transistor. So, you are basically controlling this two with a applied of a third voltage. This is what a transistor looks like. A transistor can have many functions. It can act as a switch, which means whether current flows here or not, I will determine by this terminal. I can choose to have no current flow here, does not matter what voltage you are applying. You might apply 100 volt also. Between this point and this point you might apply 100 volt, still get no current. Why? Because you are controlling that flow by the third terminal. In that case, a transistor can behave like a switch. Either it can allow the current to flow between A and B, or it can not allow the current to flow between A and B, just by controlling the knob at C. Okay, just by controlling the knob at C. So, it can be a switch, you can block the voltage, you can let the current flow, it is up to you. So, this kind of a switches are used in many applications, especially say power electronics. Okay. This switch allows you to block large voltage. Suppose I have a transistor, it is a transistor, current flows from here to there, and there is a third terminal here C, which will dictate how much current flows. But if I behave it as a switch, then between these two terminal I might as well apply even 1000 volt, still the current that will flow is almost 0 nanoamps, because this is the knob that is controlling, the parent, the mother knob. So, by that you are actually blocking 1000 volt between the two terminal. Okay. And moment you switch it on by tuning this knob at very small voltage, like say 0.01 volt, at 0.01 volt, very small voltage, you can have very high current of say 10 ampere. I am just giving an example. So, at very small voltage between these 2 points, you can get very high current 10 ampere, or you might put 1000 volt and still get nanoampere. So, it is a switch. By controlling the potential or the voltage at C, I can change this a lot, I can block, I can let current flow. So, this kind of things are used in power electronic circuits. Okay. And power electronic circuits need this kind of switches to make power electronic circuits, such as DC-DC converter. DC-DC converter is you convert one DC voltage to another DC voltage, or you want to convert an AC to DC, or an inverter from DC to AC, which is inverter. You can do all kinds of changes by using different small building blocks of these switches. So, power electronic circuits of this kind of DC-DC or inverters and converters are hugely used in so many motor drives, for example. Okay. And that can be used in railways to break a railway, to make the railways go fast. They are increasingly now used in e-vehicles that you see on the road to charge the vehicle. You see that electric vehicle posts are there, you have e-vehicles, you have two-wheelers, e-two-wheelers, you have laptop adapters, you have chargers, right, you have windmills. So many things are there that you can use the transistor as a switch. Okay. So, that is one application. Transistors have many applications actually, that is why it is one of the most fundamental inventions of mankind. It can be used as a switch, it can be used for logic or processing. All your IC, integrated circuit revolution, that has enabled computers, then laptops, mobile phones, all the integrated circuits are built around transistors. You can make logic circuits. If you have read digital and analog electronics, this NAND NOR logic gates that are there, which enable your computer chips to actually perform the tasks, the processors, the Pentium processor, now there you have the Penryn and all the advanced processors from Intel, Samsung, Apple and so on, right. All these processors you depend on logic gates, zeros and ones if you remember. All these logic gates are made possible by transistors only, mostly, okay, almost always. They are, so the logic circuits, and this is digital logic. Digital logic has allowed the internet, all the computers, everything. The digital logic is possible only because of transistor. Without transistor, you will have no integrated circuit that makes your computers, laptops and cell phones so compact and fast and efficient. It is not possible. So, transistor is the heart of that. Transistors are also used as memory units to store information. Okay. You can use transistors to store information, a combination of transistors, that is as a memory device. Transistors can be used as amplifiers, especially power amplifiers. Power amplifiers at RF frequency, RF frequency gigahertz, 10 gigahertz, 1 gigahertz, these are RF frequency. You can use the transistor as amplifier, which means a small signal at the input can be amplified to a large signal at the output. This is AC signal, by the way. So, when you have a cell phone, your cell phone has an antenna. Whenever you talk or you send an SMS or a WhatsApp or you log into Facebook, whatever, that information, the data comes from the nearest base station through air by electromagnetic waves, okay, which carry these zeros and ones in the forms of this amplitude and other modulation that you are there, that is there in the wave. But this intensity of the waves that reach your cell phones is very small, So, this has to be amplified to process the data. So that amplifier, you need an RF amplifier, and that can be a transistor. And once you amplify it, you have to process the data. There could be LNA, it's called low noise amplifier. You have to eliminate the noise. There are many stages of that. Finally you process the data. Suppose you are uploading a picture, that uploading the picture will have to again be an information that will be transmitted to the from your mobile handset to the nearest base station through air, but you need to send a large power out, so that by the time it reaches the tower, the power is very low. If your power that you are sending out is very low, then it will not even reach the tower. It will reach the tower at abysmally low power. So you need to pump up, you need to pump the power of the RF signal before you send it out to the base station. Okay. Again, for that you need an RF amplifier. It's called RF transceiver unit, transmission and receiver. It will transmit, it will receive, so that you can use the a transistor as an RF transceiver amplifier also. And there will be many other elements, but transistor is the heart of that. So there are many more applications of transistors. Transistors can also be used as sensors to sense, and that sensors can be used for many things: biological sensors, chemical sensors, light sensors. There could be photo transistors, right? It can sense things, it can be switch, it can be logic, it can be digital logic, it can be memory, it can be low noise amplifier, it can be power amplifier. A transistor has so many uses, and different kinds of transistors are there to do these different kinds of working, or different kind of device, different kinds of objectives can be met with different kinds of transistors. Okay. So transistors, loosely you can have two types of transistors. Suppose you have you have a pipe through which water is flowing. You have a pipe through which water is flowing. So water is coming here and water is flowing out here. Okay. Suppose you have two kinds of pipe, water is flowing here and water is flowing out here. There are two ways to control the water flow. Okay. One is that you have a tap, water tap that you put here. There is a screws are here. So by putting the water tap, you can either close the channel or you can partially open the channel, right? You can close the channel or you can partially open the channel depending on how much you tap it. That is one kind of transistor action, you can say. Okay, that is one kind of way to control the current. The other would be that you can change the elevation of this thing, so that for example the water pipe will be like that. Okay. So you can change the elevation of the water pipe here, so that the amount of water that goes can be controlled by this. You can make this much higher, right, and then the water may not be able to go, very little water will come out. So this is another way of changing the water flow, and this is another way of changing the water flow. These actually represent two fundamentally different kinds of transistors, and each of these categories, I can say two categories of transistor, and each of these categories of transistors will have many kinds of transistors between them. Each of these will have many kinds of transistors with them, right. So this kind of transistor where you can actually completely pinch off the water, these are like field effect transistors. Okay. These are like called field effect transistors, because you can actually completely pinch up the channel here, and where you can modulate the profile here, you can modulate the profile of the water pipe such that less water goes or no water goes. These are not field effect transistor, these are like junction transistor. These are where you actually do not apply a field. Here in this kind of transistors you apply a field, apply an electric field, we will come to that. Okay. Here you do not apply a field, you basically inject a small amount of current, to change this profile, and there thus you control the output current. Okay. So essentially this is your third terminal, this is your point A, this is your point B, this is the third terminal. Similarly this is point A, this is point B, this is your third terminal with which you can actually change the current flow. These are potential transistor, these are not field effect transistor. These where there are the transistors where you can inject a small current, you can change this and you have the transistor action. So this kind of transistors is, for example, bipolar junction transistor. There is also heterojunction bipolar transistor, we will come to that, and there are many other kinds of hot electron transistor kind of things are there. And this is field effect transistor where you apply a field to turn off the channel. Best example is MOSFET. Okay. There could be many others like MESFET, metal semiconductor junction FET. there could be MISFET, metal insulator FET, there could be HEMT, MOSFET. There are many kinds of transistors that are there. We will come to that later, and these are some of the transistors where you basically use a small current to turn off or on the channel by changing the profile. We will start with BJT because BJT is more directly related to PN junction, and because we have studied PN junction, we will now be in a good position to actually understand how a BJT can be BJT can be realized or BJT can be achieved by using PN junction to make a transistor. Okay. So, this is the basic idea of the transistor, which I hope you are able to follow now. Okay. And we will see how a BJT is a bipolar junction transistor. The word bipolar says that both electrons and holes will be there. It is a bipolar junction transistor. Okay. It is called BJT, and this is one kind of transistors which essentially changes the profile of the carriers, so that you can tune how many carriers actually go down, how many do not go, and that way you control the current between 2 points A and B. A and B is controlled by the third point C. Okay. So, essentially a bipolar junction transistor, actually 2 PN junctions back to back, sorry, okay, 2 PN junction back to back. So, this is one PN junction, let me write it in the other way, NP, and this is another PN junction, NP junction, sorry, this is PN. You join them together and make one, which looks like NPN. This is the basic structure of a BJT. So, this contact this layer is called emitter, that is the terminology. Okay. This is called collector, okay, and this is called base. Okay. So, you can see actually the current between this emitter and the collector, the current between emitter and collector can be controlled by putting a small amount of current in the base or P type. Okay. You can put a small amount of current here and control the current here. Okay. So, that is why it is a transistor. This is by changing a very small current here, you can make a large change of current here. Okay. Similarly, you can have the other kind of transistor also, which is you have a P, you have N, and you have P. So, this is PNP and that is NPN, both are BJTs only. Okay. So, you can have BJTs of both this type of configuration. We will study NPN in details. Okay. So, what happens is that if I have N, P, N, I told you that the current between this and this emitter and collector can be changed by the the bias or the small current in the base. Okay. We will come to that later. So, suppose you have this. Okay. How will the at equilibrium, how will the band diagram look? Your formula level has to be constant. This is NP. So, in NP it will look like this. If you recall the PN junction like that, this is PN, smooth, okay, smooth, same band gap everywhere. So, this is how this is conduction band, this is valence band. So, this is how a NP and BJT structure looks like. Okay. Now, how will this be a transistor? This is your emitter, this is your base, this is your collector. Okay. Now, for the BJT to operate it can be operated in different ways, but the most common way to operate it, is when you want to have some gain or amplification. Okay. And the way you operate is that you forward bias this junction, this is a PN junction, no, you forward bias this junction and you reverse bias this base collector junction. You forward bias the emitter base junction, this one, and you reverse bias the base collector junction. What will happen then? It will look like that, it will like that. If you forward bias the emitter base junction, electrons from this side will go there, holes from this side will come here, that is okay. But electrons from here will go there, and the moment they reach, and if you reverse bias this junction, if you reverse bias the base collector junction, then this will increase, no. because the reverse bias junction will have a large voltage drop here, no. So, you are injecting electron from here to there. So, the depletion, this region has become lower depletion or less depletion. Electrons will go to the base, they will diffuse across the base, some of them will recombine of course. The moment they reach the edge here, they will be quickly swept to the other side. So, no matter how much voltage you are applying here, the current will be dictated by the flow of here only. So, the input current is basically dictated by the base Fermi level, you can say, and the output current will not, the output current that you are getting here will not be dependent on the voltage that you are applying at collector here, because this determines the current. Okay. So, the electrons you are injected from emitter to the base side, they will go across the base. The moment they reach across this edge here, they will be swept to the collector side. That is how a transistor works. Okay. That is how a BJT will initially start to work. Okay. So, you forward bias the base emitter junction. So, the emitter base junction is forward biased and the base collector junction is reverse biased. Okay. It is reverse biased. So, essentially you are injecting electrons from the emitter to the base, and the base it will diffuse across the base. Okay. And some of them will recombine it because the base has p type concentration. So, holes and electrons will recombine, some fraction will reach this edge of the base collector junction. As soon as that reaches the edge, it will be quickly swept away and contribute to collector current. Okay. As soon as it reaches the edge of the base collector depletion region, of the base collector depletion, it will be swept away, and the current that you get at the output here will be those electrons that have reached here, and that do not depend on the collector voltage they are applying, but they depend on the emitter base potential difference only. So, that is how you actually depend, you can tune the current here by changing the base Fermi level here. Okay, that is what is happening basically. Of course, if all the electrons that you are injecting from here get recombined in the base, nothing reaches here, then there is no current. So, you have to make a design rule actually, you have to understand many of the things here, but this is the basic diagram of a PN junction. The controlling unit is the base, the output current is this collector current. So, I will call it JC or IC, this is the output current, this is the input current that you are putting to the base, and this is emitter which is usually grounded, for example. Okay. There are different modes of operation though, that we will come slowly one by one. Okay. So, let us end the class here today, we will go it slow on the BJT front. So, what did we learn in the class here? We have introduced the concepts of transistor. There are many kinds of transistors that we have learned today. We have transistors that do many kinds of device working. There are transistors that do memory, there are transistors that do logic, there are transistors that do amplification, there are transistors that work as switch. Okay. So, transistor essentially is a 3-terminal device where the current between 2 terminal can be dictated by the potential or the current at a 3rd terminal, that is called transistor. And we have introduced the concept of BJT as 2 back-to-back PN junction. PN junctions, 2 back-to-back PN junction, one of them is forward biased, one of them is reverse biased. The idea is that the forward bias junction will inject electrons that will diffuse across the base, some of them will recombine there in the base because the base is p type dope, some of them will reach the edge of the collector depletion. As soon as they reach the edge of the depletion, they will be swept away. So, this is the basic functioning of a BJT. We will come to the next class, in the next class, and we will step by step learn what are the different current components in BJT, how does amplification happen, and how will a BJT work, and what is the gain of a BJT. So, many things are there. So, next few lectures will be devoted to understanding BJT, okay, and where are the areas where BJTs are practically used today. Okay. Thank you for your time.